Good morning, good afternoon, or good evening, wherever you may happen to be, and whether you're watching live or archived. And welcome to another in the Nautel Transmission Talk Tuesday webinar series. I think I got the name right. Look, at this point, I have no idea. This is episode 26, or could be 27. Somebody's counting somewhere, but I just want to say thanks. I'm your host, Jeff Welton. Today, we're going to have some fun. We're going to talk about filters. I've got somebody, as always, who knows a lot more than I do, which isn't usually that hard to accomplish. But today's guest is Sean Edwards from Shively, and Sean's the Director RF Engineering. Sean, welcome. Thanks for coming with us today.
Well, thank you. It's a pleasure to be here. And
oh, look, you took the ball cap off. You're all dressed up and ready to roll.
Yes. As you can see the view out the window here, we've got our first snow. And we have, it's just a picture.
Yeah. So you are down in Maine, though. So you're East Coast. Let's see, if I looked at a map, you're actually about 150 miles west of me and just a hair south.
Yeah, we share the same climate.
Yeah, although ours is, we're cold today, but rain, no snow yet, knock on wood.
Right.
So with any luck, I am just going to mangle something on the screen now. Before we get going too much, the mandatory housekeeping stuff, folks. So anybody who's seen one of these before, and I see a whole lot of familiar names in the audience, will know that we encourage questions, comments, criticisms, concerns. You can type them in down there. You've got a little question window on your control panel, or if you hit the little hand raisey icon that's up where it says muted, then somebody who looks a lot like me can probably unmute your microphone and we will have a little conversation, have some fun. So definitely, if you've got any questions for Sean, like I said, direct them all at Sean because he's the one that knows what he's talking about. I'm just here for color commentary. That's it. The occasional comedic interlude. One other note, if you're an SBE member, this does qualify for half of a research credit under category I of the research schedule. Go to the shiny new SBE website and keep track of your stuff there. By all means, if you're not an SBE member, you should think about that. And if you are an SBE member and not certified, why not? Get it done. All right. So on that note, hey, Sean, are you an SBE member?
Yes, I am.
All right. You got a certification?
Yes, right now my only certification is CBT.
Well, there you go. We're going to have to work on upgrading that for you this year too. Wayne, I'll expect a little bit of a kickback for all the membership drives here I'm doing. Now, so Wayne Pacini, SBEC president, tends to join us, and it's really great to have him here. The SBE does some great things, and they've been really up in the game in the education department, so it's awesome to see. Anybody who's been watching the Transmission Talk Tuesday knows that I've used the same agenda slide for 27 of these now, I think, and it hasn't changed, so we'll just whip right past that. Here's the concept. So for the folks at home, this is all new to Sean. We were going to do a little dry rehearsal, and somebody who looks a lot like me didn't have anything built until, well, about 15, 20 minutes ago, so it's going to be a lot of fun as we run out. The good thing is I'm working with material that Sean provided. So, yep, we'll definitely have a lot of fun. Going to throw some credit to our disembodied voice, Ed Sylvester. Now, Ed's not with us today. He had another appointment that he had to attend to. So Matt Herden is hiding in the background. But we're still going to use for our little contest, rather, Ed Sylvester will be the disembodied voice logo. Look for the credit slide with his picture on it and tell me who the picture really is. And in this case, we're going to ask you who the picture is portraying. You'll see it you'll know it when you see it. All right. So these are the kind of things we're going to talk about. The cool thing about FM is that over AM, with AM, we've got components in the filters. We've got you know, coils and capacitors, and in FM, a chunk of pipe achieves all that because of the higher frequency and shorter bandwidth. Yeah, Sean?
Yeah, so how, addressing this question here, how is a piece of pipe both an inductor and a capacitor? Well, it's all in how you use it. So a wire has a inductance per unit length and capacitance per unit length, and in filter, we're using a resonator that's shorted on one end and open on the other. So through that configuration, we're able to work with magnetic fields, which are inductive properties, and capacitive fields, which are electric fields, which are a capacitive property. And by changing configurations and changing lengths for frequency, resonant frequency, we're able to construct a resonant network that has both inductive properties and capacitive properties.
And that's pretty cool. I mean, it's like I said, I'm an AM guy, so I'm used to seeing, you know, discrete coils and capacitors and wires joining them, but you do run into, even on AM, where the wire connecting them, depending on how it's routed relative to the cabinet, can have a coupling effect, and some stray capacitance gets factored in. So this will be kind of fun, I think. One of the slides, and I picked a slideshow that you did, and I'm going to do a shout out. I know he's not, I don't think he's on today. I haven't really been paying attention to the audience list, but Larry Wilkins down at the Alabama Broadcasters Association has done a lot of work with their engineering academy. And they do a pretty good trade show annually. Plus, Larry does several engineering academy presentations throughout the year. And definitely that's something, if you're interested in furthering your education. I know he's got John Bissett coming up very shortly from Telos doing some tips and tricks. So, you know, the definite shout out to Larry and the amount of work he's done. And the presentation that we're using as the basis for today is one that I unashamedly stole from a presentation that you did at the ABA last year, back when we were all allowed to travel and see each other in person. And one of the things that you showed that really illuminated it is, you hear all this talk about a 2-pole filter or a 3-pole filter or whatever, and I never really got, until I saw this, what the difference was from one to the other.
Yeah, so here you're seeing the 3 different traces: the blue trace, the green trace, and the red trace. And so when you have resonators, if you were to stack those resonators up without a impedance transformation or an inversion in phase between them, you just get the same one cavity response with just ever increasing loss. But by changing the phase between each resonator by 90 degrees, you can get a response that now has better and better bandwidth. So what you're looking at here, the blue trace is a 2-cavity resonator. You're only going to get so much isolation from that removed from the center frequency. By adding resonators, we're increasing that skirt isolation. And you've seen in UHF applications as many as 8, 9 resonators sometimes. And in cell phone technology, there's even more. But for our purposes in FM, 4 resonators pretty much does the job.
There, sorry, I had to unmute myself now. Kirk Harnack has already put a interesting comment in here. And Kirk, as always, rather than me try to read it all and potentially mess it up, I am going to unmute you, and perhaps I'm almost 100% certain that Kirk has a microphone.
Yeah, of course I do.
Kirk.
So you mentioned about antenna thinking of it as an impedance transformer.
Yeah, for years in my whole career, I've tried to, we as engineers, and any concept, we try to model this in our head, right? We have ways of thinking about concepts, and sometimes we're told out of a textbook how to think about something. It works like this, to something else relatable in our lives. And nobody's ever really explained to me in such a way how an antenna actually works. I wish we could see the waves coming out of an antenna like they had a color or something, right? That would be cool. But I've often thought about antennas as, in addition to this device that creates a magnetic field and an electric field, and I still don't really understand their relationship so well, but I also think of it as an impedance transformer, transforming the 50 ohm impedance of a standard transmission line, because that's what's convenient for us to have and use and build into industry standard, converting that into the natural impedance of free space. at RF frequencies. Is that valid at all, or do I just need to totally forget that concept?
No, that's a good analogy. And the part that's not addressed there is the radiation property. But when talking about the transformation between your feed system and free space, I mean, essentially that's what it's doing. It's the transformer for that. Now, what's great about today's electromagnetic software is you can actually visualize those waves emanating from a radiator. So at some point I should include that in one of my talks. But I like to, you can also think of an antenna, especially a multiple element antenna or a multiple an array, as each element, each radiator is a resonator. There's actually analogy towards filters. So if you think of the proximity between them as coupling, that's a factor. If you think of the adding them up, you get higher gain and more selectivity. That's also true in the radiation pattern. Where an isotropic will receive equally in all directions, a 12-bay antenna side mount is only going to receive, it's going to receive maximum energy because it's a passive device, transmit and receive towards the horizon. So I look at that, my way of thinking of it is more like resonators and a bandpass filter.
Cool. And I'm sorry if that question was kind of out of order from the rest of your talk, and I'll pay attention to the rest of the talk here.
No, you're good. Thanks, Kirk. Appreciate that. Now, one of the things, and I kind of clicked on it while we were talking, but you did have a pretty good video or series of slides showing the interaction of the fields, and that's what I've got clicking. So that's whoops, there we go. Getting a little carried away with myself. I'll let that run. And so what are we looking at here?
So in this video, you're looking at vector lines for the magnetic field. The magnetic field expanding and contracting. And in that series, you can see that one resonator, the first one, the input in this case, the field's expanding, and the next resonator, the field is contracting. So there's that time difference between them. You can also see there's a wall in between the resonators, and you can see there's also a vector showing, an arrow showing the coupling through the aperture, because there's a small opening between the resonators, and that's how the energy is coupled from one resonator to the next. One other thing, if you could click that one more time, all resonators in a filter are not created equal. The amount of coupling and field intensity present in each cavity is different. It can be different. It can be equal, but it also can be different. And you're seeing a 3-pole filter where the intensity on that center cavity, the second one over to the right, is much higher than the field intensity in the input cavity. And that's true. That's the currents are much higher and voltages are much higher in those center cavities on a 3-pole.
And that's something that you never really think about. You think you got 5 kilowatts in, maybe a hair less than 5 kilowatts coming out because of the insertion loss of the resonator. You don't really think about what's going on so much inside, which kind of comes back to the whole impedance transformation concept.
Yeah, you would notice, Jeff, if I could interject for a moment, that if you were to put your hand on the top of that filter, you would feel, all filters get a little warm. Some get a lot warmer than we want, but some, you would notice that the middle cavity would be warmer than the outer cavities.
Yeah. And Ira Wilner comments that an antenna is actually a transducer alternating electricity in a conductor converted to radiating energy in the electromagnetic spectrum. See, this is why I hang around with y'all, because you're smarter than I am and can say these big words without choking on them.
I like that description.
But it is, I mean, and this is the one thing that I tell folks, and we're used to hearing it for AM, because with AM, of course, the whole tower is the antenna, and that's what you think of. But on FM, that little thing up at the top is the antenna. The theory doesn't change, is that in effect, what we're talking about is the set of speakers for our stereo system. And this is something we're going to touch on in a little bit, but you know, just like the best Macintosh stereo system into a $10 set of Walmart speakers is not going to sound like anything but pure crap. A really nice transmitter and excellent studio and everything put together beautifully into a terribly designed antenna isn't going to perform nearly as well. Now, in this case, well, no, it still has an impact on audio as well. But we're also talking coverage, we're talking intermod, all kinds of things, right?
Yeah. So an antenna, you know, one of the things that we struggle with antennas is getting them fine matched on a tower. If you have a tall tower and you have a mismatch of, you know, around a 1.2, 1.15 to 1, it's usable, but it isn't optimized. And with that length in between the mismatch and the transmitter, just like in the old days, you could get ghosting with television. You can also create multipath before the signal leaves the antenna. So there's destructive phase happening with that, and that can greatly cause problems with coverage. So that's an example of just how a mismatched antenna can cause an issue.
Yeah.
You know, and when antennas fail, either something gets struck by lightning or ice hits one of the elements, you notice a change in coverage, because now that all the near field electromagnetic field that was generating your pattern to begin with is now different. So
I'm kind of going to segue a little bit away from filters for a moment, but while we're on the topic of antennas, and again, thinking of it from an AM perspective, it's less a concern because the whole tower is the radiator. But in an FM situation, you're basically mounting your antenna in front of a giant mirror.
yes, and that's where, you know, that's the struggle. You know, everybody would love to have a top mount on the antenna because that's the ideal situation. Unfortunately, that space is reserved for other bands. And normally in FM, we get to operate down on the tower somewhere where we have to deal with the tower effect. And so that's one of the benefits of doing a pattern study, to know exactly where the coverage is, you know, where your signal's going, and that it's going in the direction that you want it to go. Just an arbitrary placement, it's a crapshoot at that point.
And that brings me to something that I've experienced firsthand. I had a guy, he rarely, I mean, as a rule, we sell transmitters, and if you want a whole package, I'm going to send you to somebody qualified to quote the whole package, but we've got the tools to do it. It just takes time. And I had a situation once where a guy got an antenna quote, got the order placed. He sent us, he said, yep, it's a 3-standing guide tower or 3-foot face guide tower, this many feet tall. And we're above the top level of guy wires or whatever, I forget exactly, a pole mounted above the top, and everything was beautiful. And so the company did got the antenna built. The guy decided to save some money on the delivery by going down to pick up the antenna himself. And he shows up, and I get a call from the antenna company, and they're panicking. They're going, so this antenna that we designed to go on a pole on top of a 3-foot face guide tower is going on a 12-foot face self-supporter, and it's on a tapered section. You know, that's not an insignificant difference, even though we don't think about the tower itself being part of the antenna or part of the antenna properties.
Yeah, in that situation, you would have multiple problems. None of the mounting would fit. So you'd have to, you know, unless it was a situation where the mounts were being designed on site. But you know, that detail there, if it's again, one of the distinctions here is, are you buying an antenna for in this discussion, is it a directionalized antenna? If that was the case, we would already have had all that information. That's one of the things that we do in the beginning, is give very detailed information so that we know exactly where it's going. So in a situation where it's an Omni, then that was just a poor choice of installation locations, or a miscommunication of where it was actually going. The performance would have suffered for sure.
So I'll throw the curveball into this one. In this particular case, the customer, who is a pretty good engineer, He had filled out all the forms with all the antenna info, right down to the pipes and the wire cables going up the tower. What he neglected to mention was when they lost that site in the middle of the CP and decided to switch to a different site with a different tower, and totally forgot to bring that up to the antenna manufacturer.
Yeah, that sometimes happens, and it becomes a scramble to correct things. But
So
that does sometimes happen, and that's the right response, is to make the best out of, make lemonade.
Yep, and in this case, what they ended up doing, they ended up fabricating some offsets, pole mounting the antenna about 6 to 8 feet off of the face of the tower to minimize the reflections as much as they could. It was a really interesting challenge, but yeah, it's one of those little details that, and it comes back to something I beat the drum on over and over and over and over again, is if you're doing a project, you need to have checklists. You need to have, and because things change, what do they say? No, no battle survives the first encounter with the enemy. Well, the same is very, very true of any engineering project. So you absolutely need to have a list of it for anything that changes. Who do I have to tell?
Yeah. Jeff, just a side note on that. That same list of details for the site, when it comes to shared sites, there should be consideration given to what other stations are on the tower and where are they relative to my news system. Because that information is how we would decide what's best for RF filter for the site to prevent any intermods.
Right.
And you don't want to always buy the 4-pole filter with cross-coupling that's not, when a 2-pole filter will do the job just as well.
Right. And getting back to the filters, because that's a good way of dragging me back on track. So again, we've got some pictures of the interaction going through again, a 3-pole filter showing the highest field intensity in the center. What is this exactly? And I'm going to John Van Milligan mentioned that he's looked at filters with his FLIR, his thermal imager, and it's interesting especially if you have another station on the tower.
Yeah, we have done the same thing here. We've done a lot of high power testing of the products. What you're seeing here, and let me, I have a story for that too. But what you're seeing here is a visualization of the field. What you were looking at before, where the arrows were just magnitude, and the arrows pointing in towards the probe or away from the probe were representing the electric field, and the ones circling around the probe are representing the magnetic field. And when you look at a video of that, you can see that they don't occur at the same time, because it's that 90-degree separation between the voltage and the current. In this case here, this is the magnetic field intensity that you're looking at, I believe. Yes. And in the corners, you notice in the corners of these square cavities, there's not a lot happening there. There's essentially no field. And that was actually measured early on by Bob Surratt. He actually put a small fine probe in here and measured the intensity of the field from the center all the way out, and noticed this characteristic. So that allows you to change how you might manufacture something. Do you need a full weld along that whole side, or just a tack? Or is it a weld on the outside sufficient? So that's an interesting observation with that. And in the center here, you're seeing a couple of blobs of green energy that are in between the two resonators. And that is what you're looking at there is the magnetic energy through the coupling aperture.
Cool. Now, let's see. Question from Ira. Speaking of Ira, I don't know if you've got a microphone with you. If you do, you are unmuted, and you're more than welcome to join in and let us know. And if you do not, then we'll carry on just reading the question. But the short answer, or the Iris question was, speaking of details, how do those okay, he has no mic. Speaking of details, how do those feedback links work to enhance cavity filters? He's talking about he's got some of your branched and balanced combiners. And I know you had some comment about feedback links in the presentation that I was looking at, and I don't remember if they made it in further down or not. So let's hit that now.
So this is a great slide to leave up for this. So if you have just the 3-pole response, you're going to have what we looked at earlier, where you're going to have symmetrical skirts of attenuation up above and below the bandpass frequency. By taking some of the energy from the first resonator and coupling it at the right phase into the last resonator, you can produce a transmission 0 within that 3-pole structure. So from input to output, now you have a response that has a notch on one side of the bandpass or the other. If you need notches on both sides of the cavity, both sides of the bandpass, then we have to move to an even order filter. So a 4-pole cavity will allow us now to produce the phase introduction with that feedback loop into the last cavity, first and last cavity, and that will produce 2 transmission 0s equally spaced above and below the bandpass frequency. So it's about sampling a little bit of the energy and reintroducing it into another cavity at the right phase angle.
So I assume that one of the best applications for that would be in a short space situation where you've got somebody right on your shoulder that you need to block out.
Yeah, either from an antenna, excuse me, from antenna coupling, close proximity of the antennas and 2 separate transmitters, 2 separate, maybe even buildings, or in a combined antenna. That's where you see those used.
Awesome, excellent. All right, moving forward, I think the same basic view, yeah?
Yeah, magnetic field.
And then this got intriguing. So now tell me what I'm looking at. I mean, this was sort of, I think, same thing, different dimension?
Yeah, same thing, different type of filter. So the first one that we looked at was an iris coupled filter where you have discrete resonators and an aperture coupling, or in some cases you may use a coaxial coupling. In some cases you might use a capacitive coupling between the resonators. In this case, you're looking at an interdigital filter. And just like the name implies, I love when names are like this. Put your fingers together, there you go. You got this filter design. So what you're seeing here is remember earlier I mentioned that in order to get the bandpass response with minimal loss on the bandpass and maximum attenuation, there must be a phase inversion between the resonators. So in this case, it's accomplished with the ground plane being on the opposite side of the resonator cavity. There's no walls in this. The coupling is done by proximity of the probes to each other, and the phase inversion is done by grounding the resonators on opposite sides of the outer conductor. So you're seeing here the magnetic field is minimum at the input. So this image was taken at a time where the center resonator was resonating and neither of the input or the output was really intense field. And now this is the same moment in time looking at the electric field.
Mm.
So the magnetic field was maximum on the center probe. At the same time, the electric field is maximum on the other 2 probes. So it's there's this oscillation, 0 to 90 degrees and through the wave. And that's what you see when you automate these is that the magnetic portion of the resonator will operate and be active, and then that field will collapse and give rise to the electric field at the open end of the resonator.
So Ray Lewis wants to know, what's your favorite filter synthesis tool? He uses, I'm going to mess up the pronunciation, Mycian, and HFS?
I have never used Mycian or Mycian, whatever the pronunciation is there, but I've used ADS, which is an RF designer tool, and I've used and created filters using lumped elements with inductors and capacitors and applying a Q value to those to simulate the resonators in the network. And I've also used HFSS extensively. That's where these images are from.
Okay. Richard Redman is here. Have never experienced a transmitter salesperson suggest channel filters, which has made clients question recommendations he always makes. And I can address that one. Richard, do you have a microphone with you? Just hit me a yes or no, but I'm going to unmute you and bring you in, because that is a really good point. And it is something that we run into a lot. So the transmitter guy, guilty as charged, as a rule only looks at the transmitter. We're not looking at the rest of the site. We don't know what else is on the tower. We don't know what else may be in the channel combiner. So yeah, as a rule, I'm only going to quote what I'm asked to quote. But that's a really good point on how we can work together. And Richard, I see you're unmuted. So what are your thoughts on this? Unmuted, but I can't hear you. Okay, so Richard's unmuted, but we can't hear him, so we're going to have to carry on with the audio. Richard, if you do get your mic figured out, just holler at me, and we'll carry on from there. I'll leave you unmuted for the moment. Definitely, it is a situation where the engineer needs to be, and I say the engineer needs to be, it needs to be a cooperation between engineering and station management, so that they understand that the engineer is the guy that sees the whole picture on the ground. And the equipment vendors, of course, only know their own specific piece. I mean, I assume, for example, Sean, if and that kind of comes back to that story I was talking about before with the antenna. You know, definitely the sales or the sales guy will sell whatever he's asked to sell, but the person on the ground at the site can only be the one to address what else is there to interact with it.
Yeah, and this is a common area where it's a continual challenge to get all the information on site. And you know, for us, when we get an inquiry about a filter, sometimes it's cut and dry. Sometimes there's some questions, and there's no red flag that pops up and says, "Hey, this one needs some extra attention." So you know, we try our best to communicate with the consultant or the local engineer or the person that knows most about the local site, so that we can glean enough information to produce a combiner system or a filter that's really going to meet the needs and not almost meet the needs.
Right.
You know, that's very important, and it's always about communication back and forth, many times sometimes.
And that comes back to Richard's point, because like in a situation, I mean, I can tell you what the turnaround loss is for any of our products pretty much.
Mm-hmm.
And so if I know that there's another station on the same tower, separate antenna, and I know the distance between them, and we'll touch on that in a bit, I can figure out the isolation that way, add my turnaround loss, and from there I can get an idea if I've potentially got a need for an additional filtration. But unless I know that information, and again, it comes absolutely like you say, it's and part of it may come back to the sales guy asking all the right questions too. You know, is there anything else we need to be worried about? But definitely, especially if you're working with a system integrator or a company that sells full systems, you really need to make sure that they've got that kind of information. And Bob Trimble makes a point with our specialties, and again, talking about the system integrators, that make sure to look at the whole system, not just the individual box that got asked for. Javad asks, by using filters, am I protecting my adjacent frequencies, or am I protecting my baseband from other harmonics coming in? And it's kind of the answer is yes, right? It's a filter doesn't care whether it's a signal trying to get out or a signal trying to get back, it's going to block it.
Yeah, with some caveats there. When you look at within the FM band, that's generally true. But when you look out of band, filters have what's called harmonic response, where and that'll change from the fundamental to the harmonics by 6 dB per octave. It's approximately that, and it's going to change depending on the type of filter structure. So in this particular filter that's on the screen right now, it's a very simple structure. So there's not a lot of odd structures, coupling structures that can create resonances at higher frequencies. But in other filter designs, like our higher powered filters, the filter structure is so large and the coupling structures are so large that now you have structures in there that are resonant at other frequencies. So if you look at the out of band response for this interdigital, it's very clean. And all you see essentially up to about a gigahertz is just the harmonic responses. Everything else, there's no conduction. But if you look at an iris coupled filter, a larger filter where the components are larger and now they're resonating, and if you look at that response, it's only going to be very ideal up to perhaps the second or third harmonic. And then you get areas where you get higher conduction. They might be 10, 20, 30 dB down, but they're not 80 dB down.
Right.
So in those situations, the out of band transmission, maybe you have a site where there's a possibility for LTE interference. There could be depending on the type of filter, perfect conduction at those frequencies. So that may be something that needs to be addressed.
And again, that comes back to, sorry, go ahead.
I was just saying, again, that's site specific.
Right, and that comes back to the communication. Now, Jerry Higgins made a comment about using quarterwave stubs to trap interference and harmonics in VHF low band, and that they work for broadcast, and that's another good point. I mean, if you've got, if you don't have a close first adjacent, and maybe you've only got one other thing getting back into you, then sometimes just setting up a quarterwave stub will take care of that. For what it's worth, many years ago, I saw all of 3 or 4, I think. If you go to our website, nautel.com, and go to the technical, the support tab over to the right side of the page, under the technical resources tab, there's a tips and tricks, which is the articles I write for our Waves newsletter. If you go back through those archives, there is one on how to build a quarterwave stub. I mean, it was specifically written using, 1/4-inch coax, but the theory doesn't change much as long as you know the velocity factor of the cable, whether you're using 1/4-inch coax or 4-inch line. Doesn't make a whole lot of difference. It's just how hard it is to solder the jumper at the end.
Yeah, that's right. So I would just add one thing to that. You can think of a notch filter solution like that as a one-time solution that works for the site as it exists at that moment. If anything is added later on, then you may have to address those interactions, where a bandpass filter is kind of future-proofing. So
right.
Again, each site has its own best solution.
And the Iris got a point. I've had transmitters that needed channel pass filters, never install a translator on a tower with other radiators, FM two-way, if in or near the FM band. And that's a valid point, especially these days where most transmitters are broadband. Your turnaround loss is typically in the 15 to 20 dB range, give or take a little bit, because I mean the transmitter's designed to pass everything from 88 to 108 and then some. So do you find that over the days when filters or transmitters were very specifically tuned, do you find that that's increased the need for channel filters?
Some of the earlier transmitters, like the ground to grid transmitters, had as little as 6 to 13 dB of turnaround loss.
Well,
so
there you go.
Turnaround loss is one of those factors in the equation that is helpful, but not really to be relied on. As far as I mean, if you've got a 10 dB question, if you're going to hit your number and you're not sure about it by about 10 dB, you might need a filter there, because the antenna, we may talk about the antenna isolation can be estimated, but unless it's actually measured, and anything changes in the aperture could change that over time. So, if it's not measured, then it's an estimation, and you really should be looking to do it at least a 10 dB, probably a 20 dB pad on what you're expecting for to prevent spurs.
Yeah, and I mean that's a really good guideline. As a rule, anytime you design anything to just barely meet what it's got to meet, you end up coming up disappointed at some point or another, whether it's as things age, getting older, or whether somebody else moves into the neighborhood and the situation changes. So always best to have that extra headroom any part of the system when you can get it. Let's see, Sean made a 104.1 3-cavity bandpass filter for one of my translators on the same tower as my Class B FM at 103.7. So apparently you did a good job. Pat on the back there.
Oh, great. And that's a close, those show up a lot more, 400 kilohertz spacing.
Mm-hmm.
And
go ahead.
It's a lot easier to do that at the translator power level than it is at the higher power level.
Well, and that's the thing. I mean, the technology doesn't change, but I mean, like looking at this box, for example, the physical size when I'm dealing with 20 kilowatts versus 200 watts is going to get pretty much, it's a pretty significant increase. So that's a lot more materials and a lot more planning.
Yeah.
Now, moving forward on this.
One more point to the 400 kilohertz spacing is that in those situations, you're in a tough situation to begin with because of that situation. Is that you need the isolation. You got higher powered stations, low powered translators. They got to have that isolation to keep from generating spurs. But what's important to remember is that try to avoid that situation when you can, because a 400 kilohertz isolation in a bandpass filter will definitely affect the bandpass characteristics. And in most cases, that can be a symmetrical, you're better off with a 4-pole low-powered cavity in some cases there than a 3-pole. So it depends on, again, it depends on what you transmitted.
And that comes back also to what we were talking about earlier, where the bandwidth and the linearity of the antenna, or in this case, the filter prior to that, but the entire radiation system, if you will, has a significant impact on things like coverage and signal quality. So, in some cases, you could end up causing yourself. So I've had an AM station that was running so narrow, it was like 6-to-1 SWR on the lower sideband. And it, surprisingly enough, did not sound all that great.
Sometimes that happens.
Another comment about temperature compensation for close space filters and reject loads. Or reject, sorry.
Temperature compensation?
For bandpass and for close space filters, is that a situation?
Okay, so when in our filter designs, the lower powered filters are designed without any sort of temperature compensation. What we've done there is we've increased the airflow through the filter and limited the power to something that's usable at those, so it can rise to a certain temperature and not go out of spec. It's designed like that. Other filters like these the one that you're looking at here in our high-powered 30 kilowatt systems, they have a temperature compensation device where it's an invar rod that's holding everything right where it's supposed to be. It's a low thermal expansion, and the length of the resonator doesn't change with the temperature variation. If you don't have that in there, the temperatures that are present in a 30,000 watt filter with 30,000 watts going through it, the copper would grow. If it was just copper, the copper would grow and detune the filter and change the whole transmission characteristic. It would change it to a lower frequency. So in order to keep the VSWR where it's supposed to be and the transmission characteristic where it's supposed to be, we use that kind of thermal compensation. And when you're working with combined or close space stations, those same devices are at work for the bandpass power. When it comes to the dissipation of the interfering signal, you're usually only talking about a few watts here. It doesn't take much power to generate a spur, but it, you know, so that energy is just dissipated in the feedback structures or in the filter itself.
Yeah, so mostly you're dealing with the.
Yeah.
Now, one comment, and I'll let the commenter remain nameless, and it had an issue with the bandpass filter from an unnamed manufacturer where it was designed with fans on it, but the system was initially turned on without them. VSWR was okay at first, but started to rise, turned the fans on, and all returned to normal. And that's the same situation where the filter components start to heat up and expand and change the tuning, yeah?
Yeah, that's especially with the empirical evidence that you had, that you turned the fans on, started dissipating that heat the way it was designed, and everything came back to where it should have. In that situation, beg your pardon?
I'd say a little side note about that, but AM filters have the same thing. If you are setting up an AM ATU, you need to let it run and be at temperature for a bit, especially if you're dealing with a tight directional where the tuning is really critical, because at temperature, the tuning will be totally different than it is at ambient.
Yeah, and that's, you know, we've actually done that in the past where situation where the filter had to be tuned once it was at power. So it would come on. You saw a similar thing when in the early days of IBOC with the isolators, circulators. You had to adjust them under power, under the normal heat load. But thankfully, we're beyond that. That's a lot of extra work that's not necessary today.
Yeah. Javad's got another note here about having a situation coming up where the FM station is able to use 1.4 kilowatts during the day and 3.2 during the night. And so with that kind of dynamic and change in power, could a filter be designed to work linearly within the two different power? Because of course you got two different operating temperatures too.
For FM?
Yeah.
Oh, that's interesting.
Well, I mean, I assume, I'm going to guess that it's non-North American, but yeah, I mean, so theoretically, I mean, with your fixed one, that'd be less an issue. Beyond that, you sort of end up, what do you do? Tune for the middle?
Yeah, I guess that in that situation, the best approach would be, if it was a non-thermally compensated filter, probably the best approach would be first have it under power and tuned for the higher power, and then the lower power, and then pick the middle, because then it's going to shift essentially equally. So it's going to be equally as bad on both occasions.
And that's what we used to do with some of the old AM stereo setups, where you had day array, night array, and you know, depending on which stereo generator you use, some of them only had one set of tweaks. So you tweak it, optimize it for day, then set it to night, optimize it for night, and then move everything back to halfway between the two. And yeah, like you said, it's you just, best of a bad situation. Sometimes you got to compromise.
Yeah, and that's why we've designed these to have that stability. So no matter what you put into it, it's the same.
So flipping past the interdigital, I grabbed some random waveforms of different pass bands, and so this is almost going to be a guess what picture I took. But so what are we looking at here?
So this is let's see, this is a 24-inch cavity tuned with cross coupling, and actually it might be 95. It was actually tuned with that did not have cross coupling. This was designed, and the way we achieved this before we started doing cross coupled filters was to have two notch filters at the input of the bandpass filter. So your notch function would be accomplished at the input of that bandpass between the transmitter and the bandpass filter. And those two notches would be separated by a quarter wavelength to help with a conjugate match there. And then they would also have a shorted or open matching stub to help with the bandwidth and the matching there. And what you're seeing here, these two minimums, you're seeing one of the cavities is tuned a little low, and one of the cavities is tuned a little high. And it actually looks like might be part of a branch combiner you're seeing some of the effect of the other filter there as well.
That comes back to what Jerry was talking about with the Quarterwave Stubs, and the caveat he made was properly spaced. So
Yes.
this is the situation where, depending on how you space them and where you tune them, you can very much come up with different results.
Mm-hmm.
And I mean, at this point, we're just looking at a stock 3-pole filter, yeah?
No.
Aha! See, this is what happens when the sales guy tries to guess.
So if you notice with this trace, what you should see for a nice 3-pole cavity is everything plus or minus 200 kilohertz under a 1.1 to 1, and well under. Like usually we tune them here at the factory to be less than, right around 105 or less. So if any, takes a rough ride, it's still in spec once it gets there. So what you're seeing here is the effect of 400 kilohertz cross-coupled filtering. And this is not necessarily optimized. This looks like what it might have been one of the earlier ones, attempts at 400 kilohertz. But what you're seeing is, if you could see the bandpass, you would see the notch would be on the low side of the bandpass response. So if you're looking at the transmission characteristic, the notch would be on the low side. That's why there's such great distortion in the VSWR on the low side of that. Another thing that's happened here is that the filter has been tuned up a little bit in frequency, so that whenever you cross couple these things and you try to bring that notch in close to the bandpass, the reactance of the feedback starts to interact with the bandpass reactance, and it becomes a no-win struggle. You can't put a notch 400 kilohertz away from a bandpass without disrupting the bandpass itself. So one of the ways that we did it earlier was to shift the tuning of the filter as high up on that transmission skirt as we could to maintain good transmission within the analog portion of the channel, so that in the analog you see that it's a decent enough VSWR. It's out at the 200 kilohertz that it starts to suffer.
So again, making the best of a bad situation type deal.
Yeah, a lot of things happening with this trace.
Yeah. Moving forward, and we're going to run a little bit over, so we're going to high speed these ones a little bit. But this is just looking at a notch, and just high end of that's pretty self-explanatory on that one.
Yeah.
And same deal. This one's a little different though.
And this is actually, yeah, this is the response from the VSWR response of the trace that you just showed. And again, you can see that the bandpass itself is greatly reduced. Again, these are earlier
iterations. Yeah.
Yeah, they are. Our responses are much better than this at this point now.
So that kind of leads into something. Warren just asked this, and he was hoping to get in before we run out of time. So I think we can hit it right now. But can you talk about group delay and correction technique, and what effect filter passband has on FM synchronous noise?
So when you're looking at a couple of the aspects of transmission quality that's very important is frequency response, so amplitude variation across the channel. VSWR response, obviously, that's the most apparent to all of us, especially the two of us, Jeff. VSWR is bad. And then you get into the group delay. So if your group delay across the channel is greater than like 300 nanoseconds delta from any one point to the other, that becomes noticeable in the audio. That causes distortions that you're more familiar with probably, Jeff, than I am. I just know that, and I've talked with you about it, because some of these solutions with 400 kilohertz can give a group delay distortion of up to a microsecond. Now, that's going to be noticeable.
Yeah.
Especially if you're trying to transmit some beautiful classical music with a broad range of response. So one of the things that you can do to correct for that in a combiner, if they're close spaced, is use what's called a group delay corrector. And that's an kind of older way to do it. It's a hardware approach, where today transmitter manufacturers are doing adaptive correction to the signal. So as long as they can have a measured value with certain frequency points, that they can create a pre-distorted wave that'll at the output of the transmission system or output of the filter system will be all within a range of time that's acceptable. And our spec, when we're doing large balanced combiners, that's plus or minus 50 nanoseconds over a 200 kilohertz bandwidth, plus or minus 200 kilohertz bandwidth. So.
And that is a really good point. Folks are used to hearing about adaptive pre-correction being done as an HD radio thing, but even in analog, if you're in a short space situation or in a channel combiner where isolation may be an issue, talk to your transmitter manufacturer, because we can work with Sean or the folks at whoever's making your combiner, what you're running into, get the S21 curves and actually pre-distort the transmitter output to compensate for some of the nonlinearities in the filter. Now, flipping ahead, so this is talking about using notches, and I've got a couple more. We're just going to click through a couple of them pretty quickly, but anything you want to address on this one?
No, you're just seeing two sets of two-pole notch filters. So one set is tuned to the low frequency, one set's tuned to the high frequency, and you're using two resonators in a set so that you can separate them by a quarter wave and produce a conjugate match at the band pass frequency.
Mm-hmm. And 4-pole band pass, pretty basic there. Now with cross coupling, talk to me about that.
And now, so this is an example of how you're getting notches on both sides of the transmission, your band pass transmission. And these are at 400 kilohertz. So what you see, here's an advantage here to the 3-pole option, is that this is symmetrical. So the distortion is symmetrical in the group delay. The distortion in the frequency response is symmetrical. And so there's benefits to doing this 4-pole, again, site specific. Some of the differences between using notch filters. So if you needed a notch on both sides there, you could do it this way, or you could do it with notch filters. The notch filter arrangement will have better group delay performance and better band pass loss numbers than the band pass filter with cross-coupling response. So again, site specific. This may be right for some places, but a notch cavity arrangement might be better for another site.
Right. And ultimately what they all come back to, and the same talking about the conjugate matching, and I think there was another one, about the again matching, but it all comes back to working with your manufacturer, and the better picture you paint of what they're dealing with at the site, the easier it is for guys like Sean to come up with a solution that'll work cleanly.
Yeah, that's what we try to do. Is we spend a lot of time trying to make sure we're selling what you need, rather than the fits all, one size fits all.
Right. And I mean, this one, I like this one just purely for the symmetry. I mean, this is one of the tidiest looking things I've ever seen. So that was kind of cool. I'm going to skip ahead just a hair. This was one of the other things we deal with a lot, because when you're trying to figure out what your chances are of having Intermod products, the first question you're going to get is, what's the isolation? And so you actually provided the math on how to figure it out.
Yeah, so, and this is based on a half-wave dipole. So if you're looking at vertically separated antennas, this is the formula to calculate based on lambda, an estimation of what the coupling between, and it's simplified. It's not taking into account side lobe gains or gain of the antenna. That is also another form of that. So I think that was on a different slide, but.
And I mean, so you've got a nice little graph. Anybody who wants a copy of this, this will be, and I'll mention it again later, but it will be archived so you can always grab it later. And here's one for horizontally separated. Now, I assume this is talking about like adjacent tower type situation.
Yes, and you'll notice that this one does take into account the gain of the antennas, and when they're at different elevations, perhaps a side lobe. So that allows you might have to have, again, sometimes these things open up more questions than you started with. So now you have to know the antenna patterns of both of the antennas in question in order to get a more accurate number. So right. Estimations, these are good for estimations.
Well, and again, it gives you a ballpark. So you know, if you see an answer that's kind of close, then you know you've potentially got a problem. If you see an answer and it says, oh, you're 100 dB away, then not a problem at all.
Right.
So that's absolutely something to think about. William Harrison, while I flipped through these, made the note that he had a good experience with you on site optimizing a 4-station branch combiner in DC. So he just wanted to give you a shout out there.
Oh, that's great.
So 2 frequencies into the same antenna.
Right. So they're separated by 2 megahertz. They're into the same antenna. There's no isolation there. Your filter needs to provide at least 46 dB. So if you're looking at the resonator, if you look at the chart below there, you're going to have at 2 megahertz, you're going to have about 40 dB with a 4-pole filter. So you're almost there, but not quite. So that's where you're looking at that transmitter turnaround. That could help. Depends on what type of transmitter it is. What you're looking for is the result here, at least attenuation to the spur frequency of at least 80 dB. Yeah. So to keep that below the required value. So in this situation, there would be a 4-pole filter, maybe with cross coupling.
Right. And so same deal here. And then if you've got them even closer with 1 megahertz, then things change a little more again.
Yeah. So you start looking at what your antenna is providing, what your filter can possibly provide, and that can tell you whether you need cross coupling or a 3-pole filter, or these are the things that we ask and why we ask them.
Right. Now, one of the things Iris asked is, what about circulators, isolators, things like that?
Oh, those are a really good solution for those tight situations that you find yourself in sometimes, where the only location that you can find, there's a lot of high-powered or close space stations and you're trying to shoehorn a new antenna into the only available space on the tower. And the only way around this is filtering, and perhaps that's going to do it. A circulator might do it, but what's nice about a circulator, and the way they were really used well in my experience, was during the early days of VSWR, where you had the same frequency that was coming coupled through the antennas. You needed to shunt that to the load. So it wasn't the reflected energy from the mismatch that you're using the circulator for, because that's another use for it. When there's a high reflection, right, you can shunt that reflected energy to a load. But in this case, analog to digital combining, when you needed to shunt that analog energy that was coupled over into the load so that it didn't mix in the digital transmitter.
Mm-hmm. So. And Ray Lewis makes a good point too, that ferrites can also generate some harmonics. So there's again care and caution without the you don't just blindly jump into any one size fits all type solution. Right. So that is definitely something to be aware of. Now here we're looking at again another spectrum sweep, same basic deal, right? A pair of notches.
Actually, this is an input-to-input isolation of a branch combiner system. So what you're seeing here is the transmitted, how much of frequency A is getting into frequency B, and it's a passive device, so this signal path is, the response is the same looking one way as it is the other. And for these two frequencies, 89.7 and 90.7 within a megahertz, you're seeing the result of the cross-coupled notch adding the isolation to what would normally be only, if you look on that skirt value, let's see, minus 10, 20, let's see, 30, you would only have about 35 dB of isolation without those cross-coupled notches. And in this case, transmitter, you have that augmented isolation, and that's certainly enough to prevent spurs.
Right, good. Now, so this is a couple other points that you'd made there, and this comes back a little bit to the comment earlier about translators and big antennas, and the things to kind of look at.
Yeah. So, and this slide's addressing the situation where you have an opportunity to pair onto a antenna, but there's the big disparity between the power levels. So you can't just stick a 250 watt filter that's designed for those power levels and those voltages in a combiner with a 25,000 watt transmitted signal, because the energy coupled into that little type N line going to the little filter is just going to arc over and burn instantly. So those are the limitations, and we take a look at what the filters can handle for voltages and the line that connects them to the star junction for each filter, and we can design them so that fusible link won't occur. So that's something that we look at. You have to look at the voltages present.
Well, and we had a situation once where, and just story tales out of school, so to speak, but somebody without any consultation at all put a translator at about 100 watt ERP, put that antenna about 10 feet below the bottom bay of 100 kilowatt. So even at 20 dB isolation, they were pumping more power back into the output of the 300 watt transmitter than it was qualified to handle going forward, let alone backward. It got pretty melty pretty quick. But so
that would have been a great use of a circulator and isolator at the right power handling.
Well, and that's what it ended up being, the ultimate solution. The funny thing was they also burned up a circulator, because they put in a circulator rated for 300 watts when, again, there's over a kilowatt coming back. Right. So you definitely, you've got to look at your summary. What are we dealing with?
So my advice is communicate as much as possible amongst your site engineer, the consulting engineer, and your manufacturers. And that way you're going to be able to have a site-specific picture of what is required to give you for the least amount of money, give you the best performance at the site. So looking at antenna isolation, the power levels, and antenna placement and that sort of thing.
Oh, I'm going to give a shout out to Al Dalhousen, who was the first guy to guess that specifically that what we were looking for was the guy in the Ed's little picture was from Northern Exposure. He's a DJ at the radio station there, and the character he played was Chris Stevens. So Al, thanks for that. But honorable mention to John Milligan for noting the SM7 without the windscreen on it. So let's see, Richard Redman just wants to thank you for the presentation and for building excellent combiners and great filters. So definitely there. By all means, this webinar, as with all our webinars, will be archived. You can get to it on the webinar page through resources tab on our website. We come out with the Nautel Waves letter every 3-4 months, or whenever Fiona finally drags some content out of me for a tips and tricks article. And certainly go to our YouTube page in addition to the webinars and that are also archived there. Customer service has got some helpful little videos on how to do some of the routine things that you may not always think about. One other thing to think about, we are taking a short break for the holidays, so I'm going to spend Christmas with my family, and hope you all have a very Merry Christmas and Happy Holidays, and we will see you sometime in January. Keep an eye on our website. We'll put the note up when we resume these in January. Sean, on that note, I want to thank you very much for spending some time with us today. It was a lot of fun.
It was my pleasure. Thank you. Thank you for giving me the opportunity.
And it's been a great day. And folks, on that note, again, happy holidays to all. Thank you very much, and we'll see you next time. Bye now.
Bye-bye.